In this video, we are solving a generalized Fresnel integral. We have this integral from 0 to infinity, sine of x to the power n dx. In one of my previous videos, I have solved a Fresnel integral for n equals to 2 using Laplace transform as well as beta gamma functions, which you can see over here turn by turn. Yeah, and in this video, let's solve for the generalization using Ramanujan's master theorem. But before we begin, let me introduce you to Ramanujan's master theorem. May I have the pleasure to do that? Yeah. Okay. So Ramanujan's master theorem says that if we have a f of x, if we have a function f of x in the form summation from n equals to 0 to infinity, phi of n is a function minus x to the power n by n factorial. So if you have f of x in this form where phi of n is a function of n, then integral from 0 to infinity x to the power s minus 1 and then f of x dx is actually gamma of s multiplied by phi of minus s. So this is the statement of Ramanujan's master theorem. And to just see this, to just verify this from a well-known example that we know, we can use it to verify one of the formulas from Laplace transform, that integral from 0 to infinity e to the power minus st t to the power x minus 1, yeah, e to the power minus st t to the power x minus 1 is, we know, gamma of x divided by s to the power x. So you can use this thing. This is our dta. So you can use Ramanujan's master theorem first to verify this property, right? So over here we have f of t as e to the power minus st. Yeah, we have f of t as e to the power minus st. We have over here t to the power x minus 1 dt. Yeah. So from Ramanujan's master theorem, what it says is this integral from 0 to infinity t to the power x minus 1 e to the power minus st dt should be actually gamma of x times phi of minus x. But what is this function phi? To know the function phi, we have this f of t. We need to go into this f of t, which is e to the power minus st. So f of t equals e to the power minus t. This will give us the required phi function. We should first express f of t in terms of the summation that we have. We need to express this in terms of this sum. N is equals to 1 to infinity, and here we need to have phi of n and minus t to the power n by n factorial. Okay. So in the actual expansion of e to the power minus st is summation from n equals to 1 to infinity s to the power n minus t to the power n by n factorial. So we see that phi of n should actually be s to the power n. Yeah. So by comparing the actual series of e to the power minus st in the series that we need to have, we can see that phi of n is actually s to the power n. Yeah. So this integral, according to Ramanujan's master theorem, should be of gamma of x, and phi of n is s to the power n, so this should be s to the power minus x, and that evaluates to gamma of x over s to the power x. You see that this is actually the result that we have in Laplace transforms. Yeah. So see that Ramanujan's master theorem actually works, and now we will put into application for this integral. Okay. So for this integral, let me just erase the part where we verified it using a well-known integral from Laplace transform. So we are now doing the integral. But before we begin with the integral, let me just tell you for which values of n does this integral converge. Yeah, for the values, if the n equals to 1, the sign of x actually doesn't converge because it just goes on like this, and area, it just covers area in so equal areas till infinity. So for n equals to 1, it doesn't converge. But when we have n greater than 1, so the area just gets narrower and narrower and narrower and narrower. Yeah, yeah, like this, and eventually there's no area covered during its spinning. Okay, from during its to and from motion, there's no area covered. That means it will eventually converge. So for n greater than 1, this integral will converge, but for n less than equals to 1, it won't. Now, after we have discussed the convergence, now we are ready to solve this integral by using Ramanujan's technique. So we have integral from 0 to infinity, and we have sine of x to the power n dx. Now we first try to simplify x to the power n over here, since sine of y is going to be our f of y for the to find the function phi. Okay, so we will first let y equals to x to the power n, then we would have y to the power 1 by n equals to x, and then 1 by n, y to the power 1 by n minus 1 dy will actually be dx. Yeah, and then we can make that substitution. When x equals to 0, y is equals to 0. When x equals to infinity, y equals to infinity. And here sine of y, and dx is 1 by n, y to the power 1 by n minus 1 dy. We can take 1 by n out, and that gives us integral from 0 to infinity y to the power 1 y to the power 1 by n minus 1 sine y dy is the required integral. Now we'll compare it with the actual Ramanujan's required integral, that was 0 to infinity y to the power s minus 1 f of y dy is actually gamma of s phi of s, and we get this phi function. We get this phi function from phi function. We get this phi function from f of y. Yeah, from f of y we get this phi function. Now we need to go into the phi function, but for this case, the answer should be gamma of 1 by n and phi of minus 1 by n. Okay, so this should be the answer, but for pi function we need to go into sine y now. Now we will go into the sine y and to find pi function. Okay, so we need to express sine y. Yeah, we need to express this f of y in the following form. We need to express this in the following sum. Sum from n equals to 0 to infinity phi of n minus y to the power n by n factorial. That is, this sum comes out to be at phi of n. Here's when n 0 is should be 1 by 0 factorial, and at n equals to 1 minus phi of n y by 1 factorial plus phi of n y square by 2 factorial minus phi of n y cube by 3 factorial, and then we will continue this and we will have plus phi of n y to the power 4 by 4 factorial and so on. Okay, so we need to have f of y in this sum formula with the required phi of n, but in actual sense sin of y is actually x. Yeah, so let's say summa 0 plus x is x, and then again minus plus 0 is square plus 0 times x is square minus x cube by 3 factorial. I guess you know this expansion of sin x. Yeah, you need to know this expansion. You can just Google for the expansion or use Taylor expansion, or anyway you should know this. 0 times x to the power 4 2 factorial, you can just say, anyway it's multiplied by 0, so that doesn't matter. And here now minus, so it's plus now, plus 0 times x to the power 5 by 5 factorial and then it should be over here, not 0 over here, it's 1 over here. Okay, sin of x is actually x minus x cube by 3 factorial plus x by 5 factorial. Now 0 times x 6 by 6 factorial, and but then after plus 1 over here, it should be minus 1 x to the power 7 by 7 factorial. So this is the actual series expansion of sin over y, as we know. So from here we can see that this is actually pi of 0, pi of 1, pi of 2, pi of 3, pi of 4. Okay, so we see that phi of 0 should be 0, and phi of 1 should be for this case phi of 1 should be minus 1, and then 1 it goes to this form. Phi of 1 should be minus 1. Phi of 2 should be 0. Phi of 3 should be here's minus, that should be 1. Phi of 4 should be phi of 4 here's plus, here's 0, 0. And phi of 5 should be, in this case here's here should be minus phi of 5 per factorial, but here is plus, so phi of 5 should be minus 1. Okay, now from these values we will try to we will try to figure out what phi of x should be. Yeah, so it's 0 for 0, it's minus 1 for 1, it's 2 for 0, it's 0 for 2, it's 1. Yeah, it seems like some sort of rolling up and down function, oscillating functions, of course trigonometric functions. And how can we adjust those trigonometric functions to give this value? 0 1 okay, so 0 1 0 minus 1 0 1. Yeah, it's just negative of, it's something like this. Phi of x is, it's just negative of sine of pi by 2x. And you can write sine of pi by 2x actually gives 0 1 0 minus 1. Yeah, over here 0 1 0 minus 1 0 1 0 minus 1, but it's just negative 0 minus 1 0 1, so this function works for pi of x. So now we have the function for pi of x. Now we can find out phi of minus 1 by n. Okay, now we'll just substitute over here. The answer for, yeah, okay, and I have missed something. For this integral we also have 1 by n over here in the beginning, so we'll also have 1 by n over here. Okay, and after this we have phi 1 by n, gamma 1 by n, and we have this phi function now. Phi of x was actually minus of sine pi by 2x. Yeah, so this will be minus of sine pi by 2, and our input x is over here minus 1 by n. Minus 1 by n. This minus comes out and just cancels. This 2 will just cancel out. We have 1 by n. 1 by n, gamma 1 by n, and sine of pi by 2n. So this is the answer for generalized Fresnel integral. This was indeed a long journey, but it was fun nonetheless. Phi of 1 by n, phi gamma 1 by n, sine pi by 2n. Okay, so this integral over here is actually equals to highlighted here. So now we get that integral from 0 to infinity sine to the power sine of x to the power n dx is equals to 1 by n gamma 1 by n sine of pi by 2n. So in our Fresnel integral over that can be the video that is linked over here in the card. So in that video we proved that for n equals to 2 the integral was actually root pi by 2 root 2. So we will try to prove from here too. When n equals to 2 we have 1 by 2 gamma 1 by 2 sine of pi by 4. So when n equals to 2 it's pi by 4. Now 1 by 2 gamma 1 by 2 is just root pi, and sine of pi by 4 is just 1 by 2 root 2. So sorry, so it's 1 by root 2. And now if we multiply this we get root pi by 2 root 2. So you see this is in fact true. This should be, because we haven't done anything wrong. Okay, so we see that we have solved the generalized Fresnel integral by using Ramanujan's master theorem. I hope you got how do we apply the Ramanujan's master theorem as well. And yeah, I give you an assignment or something to try upon. Solve for the cos. Solve for cos of x to the power n dx, and evaluate for x n being 2, and when n equals to 2 the answer is root pi by 2 root 2. The same answer. Just try to evaluate that, and that will be a good thing to do. Okay, thanks for watching. Hope you had a great day ahead. I look forward to seeing you in the next video.